So fundamental types of crystalline solids. We're not talking about amorphous solids here, we're just talking about the crystalline ones. Excuse me. We take crystalline solids and divide them into three groups based on what the smallest particles are. So we have molecular solids, where the individual units are molecules, and we have ionic solids, where the composite units are formula units of ions, a cation and an anion. And then we have atomic solids, and here the composite units are atoms. And these atomic solids can be further divided into non-bonding, metallic, and network covalent types. So the molecular solids. A molecular solid is composed of molecules. Okay? Examples would be ice, which is solid water, dry ice, which is solid CO2. You have individual molecules. The individual molecules are held together by intermolecular forces. Dispersion forces, dipole-dipole forces, hydrogen bonding, some combination of those. Those intermolecular forces are relatively weak, and so molecular solids tend to have low to moderately low boiling points, or melting points as well. Many of these are gases at room temperature, or at most liquids at room temperature. So things like benzene and toluene, these only have dispersion forces, and so their melting points are quite small. They melt at low temperatures. Some molecular solids can crystallize into different structures. They're called polymorphs, so many shapes. It's the same molecules, but how they are arranged in that crystalline solid are different. And this can cause it to have different melting and boiling points, different solubilities, different densities, etc. This is important in pharmaceuticals because different polymorphs of the same substance can have very different physiological activities. You may have one polymorph that does an excellent job of killing the virus or the bacteria in your body, another one that just doesn't really do anything. And so the distinction is important. I'm not going to test you on this, but I thought this was pretty interesting. There's a little sidebar thing about chocolate. You ever opened a bar of chocolate and it looks like this? It's got this like white stuff on it, and you're like, ew, what is that? It's called bloom, okay? And it's not mold or anything, it's just something that chocolate does. And here's a piece of chocolate that does not have bloom on it. I learned something reading through this earlier this week. There are actually 6 different crystalline polymorphs of cocoa butter, which is the main compound in chocolate. And they have different melting points varying from 17 up to 36 degrees Celsius. So some of these are going to be very soft. They're going to melt in your hand. Others like this, the 33.8, is not going to melt in your hand, but it will melt in your mouth. And they're going to have different densities, different stabilities. And so making chocolate is trickier than you would think. And if you've ever tried to make candy, you probably recognize that it's very easy to completely screw it up. It's much harder than, making soup or baking something even. Because to make the chocolate, I don't think I put that graph in there. To make the chocolate be this polymorph 5, which is the best kind, you have to heat the chocolate and then let it cool down slowly. But as it cools down, it forms all these different types of crystalline solids in there. So you get it partially cooled down, and then you heat it up just a little bit so that these ones with the lower melting points melt again, but number 5 doesn't melt. So you still have some of this, and those act as seed crystals so that as you cool it again, as the chocolate solidifies, it will attach onto those seed crystals and crystallize in that polymorph. And so there's a lot of art in making good chocolate. Ionic solids have ions. So examples are things like table salt, calcium fluoride. You've got calcium ions and fluoride ions, sodium ions and chloride ions. These are held together by ionic bonds between the cations and anions. Are ionic bonds stronger or weaker than intermolecular forces? Stronger. Oftentimes they're stronger than covalent bonds as well. Very strong. So very strong forces holding the ions together gives us high melting points. So ionic solids have high melting points. Some of them are crazy high. And we're going to talk about those later in a separate section. Then the atomic solids. So here you have the units being atoms. So these are all going to be elements. Examples would be solid xenon, solid iron, silicon dioxide. You might think, well, isn't that a molecule? Actually, it isn't, and we'll look at that one separately. Non-bonding atomic solids. So these do not have any bonds. No metallic bonds, no covalent bonds, no ionic bonds, no bonds. They're just held together by dispersion forces. The individual units are atoms. They can't have dipole forces or hydrogen bonding. So weak dispersion forces. These are going to have a very, very low melting point. They're going to form closest packed structures that will maximize the coordination number and minimize the distance. I didn't finish that. Minimize the distance between the atoms, I think is what it's supposed to say. I have to fix that. They're going to have very low melting points. But the melting points will increase with molar mass, because as you increase the mass of the substance, the molar mass, the size of the individual atoms, then the dispersion forces become greater, and they're held together more tightly. There are very, very few examples of non-bonding atomic solids. The only examples are the noble gases. So argon, you can make argon be a solid below negative 189 degrees Celsius. Xenon is a solid below 112 negative degrees Celsius. Those are non-bonding solids. Then we have metallic atomic solids. These are held together by metallic bonds. These are going to be the metals. Crazy. These are also going to form closest packed structures. So either that body-centered or that hexagonal closest pack. So nickel is an example, zinc, any of the metals are going to do this. And this is an illustration of the electron C model of metallic bonding. So you have an ion with its electron, but that electron is free to move. And it's the attraction between all of those electrons and the individual cations that holds the metal together. The melting point is going to depend on how strong the attraction is between those ions and their electrons. So some of them, like mercury, are room temperature liquids. Gallium will melt in your hand. But many of them melt at very, very high temperatures. So melting points can vary. And then we get the network covalent atomic solids. These have individual atoms, but they're held together by covalent bonds. Examples are diamond, graphite, and silicon dioxide. Here the crystal structures are limited by the geometrical constraints of the covalent bonds. So we talked about bonding theories, right? And we learned that carbon often has this tetrahedral form because it has 4 unpaired electrons, and it'll make this sp3 hybridization. And so carbon wants to have 4 things bonded to it. It's not going to want to be in one of those closest packed structures where it's in direct contact with 12 other atoms. It can't do that in a network covalent solid because it has to form bonds, and it can only form 4. So the crystal structures are not closest packed. These tend to have very high melting points because covalent bonds are very strong compared to intermolecular forces. So then we should be able to answer questions like this. What type of atomic solid is Au solid? Metallic. So it's an atomic solid. We know that it's an element. But what type is a metallic? Whoa. I want to draw with that one. It's metallic atomic solid. Because it's held together by metallic bonds. Which of these solids would you expect to have the highest melting point? A, magnesium oxide. So what we need to think about is what's holding these things together, right? This is, my pointer, there it is. This is ionic, right? Magnesium and oxide ions. An ionic solid is ions held together in all directions. So ionic bonds are very strong. What's going to hold I2 molecules together? Dispersion forces. I2 is a nonpolar molecule. The only thing that's going to attract it to another I2 molecule is a dispersion force. And then krypton, what's going to affect krypton? What's going to attract krypton atoms to other atoms? Again, just the dispersion forces, right? So we've got ionic bonds, dispersion forces, dispersion forces. Ionic bonds are the strongest, so we expect that to have the highest melting point. Any questions?